Our next speaker is an EGSA member, Edmund Campion. As technology demands increase, the North American grid continues to age and become obsolete, and because natural disasters and weather events are coming more frequently in a more alarming intensity, temporary power grids are becoming ever increasingly utilized when the power in a particular application has to stay on. Edmund is an industry veteran in the field of temporary distributed grid power. He began his career in this field during the late 80s, where he worked to provide temporary power for large stadium concerts and live television shows. Since 2005, Edmund has been with APR Energy, where he's currently responsible for R&D, recips, BOP, T&D, plant designs, etc. He also holds patents for scalable modular temporary power plants and containerized natural gas gensets. Ladies and gentlemen, please give a nice round of applause for Edmund Campion of APR Energy.
All right, that was a very nice welcome. Know a lot of you over the years, having dealt with you in different lives and different businesses. And it's good to see old friends here again. So background on me and background on our companies. We did fast-track power in the entertainment industry, as Charlie mentioned, and that enabled us to learn how to package, rapidly deploy, mobilize, tear stuff down, and move it around. And over the years of doing that, we moved into taking that into grids. Doing that on utility scale, where you're signing up a contract with customers and you have 60 to 90 days to put large amounts of power on the ground that's scalable, reliable, and is very efficient in what we do. The products that we use today are diesel power modules or gas turbines, and it depends on the application of the customer, and the fuels that they're going to provide us will dictate the type of products that we roll out into our applications. Most of the work we're doing today is in the developing world, around the developing countries around the world. We don't do very much work here in the US. As we're all aware, we've got a very, very solid grid here. The voltage is on every day, the frequency is stable, and we can rely on it. When we go out into the third world countries, the developing world, that is not the case. The amount of penetration out there with utilities is very, very low when it comes into the amount of energy that you have per head of capital. So today we're doing about power all over the world. We're doing power for about 25 million people in the developing world. That helps those economies. Without power, you don't have industry. Without power, your kids can't do their homework at night. Without power, you can't cook your food. So it becomes very, very important. A lot of our customers, whether they be the ministers or the Minister of Energy, realize that their economies cannot grow, they cannot be an industrialized country if they don't have energy. So it's very important for them. A lot of the countries that we deal with, they have limitations on capital. They're not able to afford to build their power plants. They want something temporary, and they can afford to pay for it by what we call pay for it by the drink. They can't buy the bottle of water because it's hundreds of millions of dollars, but they can afford to pay for it on a monthly basis to ensure that they have power on their grids. So with that, I'd like to do just a short little video, give you an idea of what it is and where we operate at.
Economies can't grow in the dark. It has been estimated that electricity shortages cost the global economy more than $500 billion each year in lost GDP. These shortages exist in both emerging and developed markets and have a fundamental impact on economic growth, political stability, health, education, and overall quality of life. In fact, almost 20% of the world's population has no access to electricity at all. The causes of these power shortages are driven by a number of factors: lack of investment and aging infrastructure, rapid development and urbanization, decommissioning of outdated power plants, natural and man-made events, and changing weather patterns. But building a new power plant typically takes 3 to 5 years, and due to severe lack of funding, many new projects cannot even break ground. That's why new power plant construction in some parts of the world is at an all-time low. However, thanks to mobile technology and advancements in plant design, there is a solution that helps cities, industries, and economies get the power they need quickly. With APR Energy's fast-track mobile power plants, entire cities are powered within days, not years. APR Energy combines speed, scale, and technology to build turnkey power plants that are tailored to each customer's requirements. Through our strategic alliance with GE, APR Energy uses the latest mobile turbine technology available. This turbine technology is used in many permanent plants around the world and relied upon by some of the most well-known and dependable aircraft in service today. APR Energy's power plants can operate either on an interim or semi-permanent basis and can deliver incremental electrical capacity equivalent to a traditional power plant. These power plants are flexible enough to integrate into permanent infrastructure and provide grid stability to regions as remote as the Sahara Desert, or deliver urgent emergency power following a natural disaster. Most importantly, because APR Energy builds, owns, operates, and maintains its plants, customers do not need to worry about upfront funding or financing. They simply pay for power. Following our purchase of GE's turbine rental business, APR Energy is now the world's largest supplier of fast-track mobile turbine power. With over 2.5 gigawatts of projects executed in more than 25 countries around the globe, APR Energy is a company customers trust to deliver power fast, when and where it is needed. The reliable electricity we provide powers millions of homes, helps industry grow, and improves people's lives. We help keep the lights on because economies can't grow in the dark. APR Energy, powering your progress. Learn more about APR Energy and our mobile fast-track power solutions at aprenergy.com.
So what causes the needs for a lot of this is we have constraints in the grid, transmission lines. We hear about that even here in California, where they can't move power north and south, up and down the corridor. It even gets more strategic when you go into developing worlds. Instances like Argentina, very, very large country, 2,500, 3,000 kilometers end to end, good infrastructure, 500 kV grids, but no generation capacity throughout the grid to keep it supported. Forced outages. Accidents happen. Power plants get damaged. Substations get damaged. This is an example of a 30 kV substation. Severe fire damage wiped out the whole substation and took 200 meg of capacity offline. You don't replace that in days or weeks. It's going to take a year to come in, buy all the new equipment, demolish the existing infrastructure and replace it. Transformers fail. Big power transformers, you're out 100, 200 megawatt if you have a critical transformer asset fail, and they can fail for multiple reasons. In this instance, the bushings failed. This one, there was an internal incident inside the transformer and ruptured the transformer. Same thing, end result is lost capacity on the grid. Same thing again, power plants, unscheduled outages, machinery's offline or offline long term. The developing world can't afford to do all the maintenance on their equipment. There's no funding. The funding's being appropriated elsewhere, and the grid loses its capabilities and loses its reliability. Buying and building new power plants can take 3 to 5 years. Putting in a temporary power solution, as we saw in the video there, can go on the ground in a matter of weeks, including all the T&D that goes with it. Here we're showing a project in Uruguay. And in the background here, you can see it, there's all the 150 kV infrastructure as well. So we talk about temporary power. You can't put the power up on the grid unless you have all the infrastructure to go with it as well. So it's a complete jigsaw puzzle, or as I like to call it, it's Lego building blocks. The power generation is one portion of it. Then you have all the cabling, you have all the transformation, you have the interconnects to the utility, you have all the protection devices to make sure it's all done. There's all the engineering to go in behind that as well, doing grid impact studies, making sure that we don't impact the grid doesn't impact us. We don't have any issues with fault currents, that if something does go wrong, the devices can clear it. And we all know that when we're dealing with generators, we have to go look at the sizing of the breakers on our generators, depending on the application, to make sure that the KA ratings are correct. If they're not, and there's a fault, the breaker doesn't trip. It's the exact same thing when we go in and looking at large power plants. We have to go in and evaluate that all the way through. Depending on the fuel source, we have the options of, do we do gas or diesel? In this particular application, we're looking at 100 megawatt at 33 kV in just outside Mandalay in Myanmar. And the project went in groundbreaking to power on the grid 60 days. A lot of time in shipping, a lot of time with our subcontractors, our suppliers, working with Caterpillar to make sure that the product was available for us when we need it, working with in-country resources, hiring as much local labor as we can in-country, putting money back into the infrastructure, creating jobs, making sure that economy is growing with us as well. Summer peaking. As I said earlier, power plants do take forced outages. In the middle of the summer in the Mediterranean, you're going to impact your tourism industry if you can't keep the lights on and the air conditioning running in your hotels. That's not good for business. Being able to come in and put in 120 meg at 132 kV on the grid in a matter of weeks solved the problem. Summer peaking, when we talk about it here in the US, is the same thing. We've got grid capacity constraints. We'll come in, as various people know, putting in temporary distribution generators into substations and put 5 or 6 megawatt into a substation to take up that area and free up the main high voltage transmission lines to put the power into the big population densities by taking the rural load off of the grid. Speed and flexibility. A lot can be accomplished when you're coming in doing temporary power. It's not under the scrutiny of all the regulators. You still have to comply with World Bank emissions. You still have to apply for permitting, but it's a temporary solution till the main infrastructure gets built. So putting it in a time scale, we can do in weeks with temporary power, having all the logistics in what takes permit infrastructure years to accomplish. It's not the cheapest, because we all know that when you're doing temporary permanent power, everything is done with finance. You're looking at every dollar you're spending. You're fine-tuning all your engineering to take every little cent out of everything, because you're going in for a 30-year opportunity. When we're doing it, speed is the most important thing over cost. Yes, we have to be cost-effective, but speed is everything. And when we talk about temporary power, I consider ourselves more of a logistics company than a power company. Moving hundreds of containers, hundreds and hundreds of tons of equipment, and getting it from point A to point B, and getting it all across the infrastructure in that country, doing site routes, surveys. Are the roads capable of carrying all those weights? Are we any issues with bridges? Do we have overhead restrictions? What's it going to take us to get stuff out of customs? Those are all the challenges that are hidden when we talk about temporary power. Dealing with governments, it's challenging. But if they need the power, they help facilitate and take down some of the barriers so that we can get power on for them and keep them elected as officials, which is rather interesting when we see governments going up for elections, just like we're hearing here in the US, and Mike talked about it this morning. It's even more so in the developing world. If they can put power on the grid, they win the votes. They stay in office. If they can't do it, the people are ticked off. I'm coming home. There's no lights. There's no air conditioning. Why should I vote for him? It's a different dynamic. So looking here at the scale of it, this is a turbine example. We're running on liquid fuel. And we go through on the left-hand side, we've got fuel coming in from the supplier, from the customer, into storage. One of the challenges we have with fuel in third world countries, developing world, is the quality of the fuel. We're looking here in the US, we're looking in Europe, we have low sulfur, very, very clean fuel. That's being regulated by the EPA to make sure that what's going into the diesel engines comes out clean on the other side as well. When you start going into developing world, they want the cheapest fuel, which is not necessarily the cleanest and most reliable fuel source, but we have to deal with it. Talking about rapid deployment, so we have, as you saw there, turbines, a 25 megawatt footprint can be put in Antonovs and moved very, very fast. Yes, it's expensive. An Antonov is roughly about $1 million a lift. But if you can get power on in days versus waiting a month on sea freight, it's a viable financial solution. In going with that thought process, what we're seeing there right behind the turbines is 20-foot ISO containers. Each one has a 10 MVA cast coil transformer. So environmentally friendly. Put 3 of them together and you have a 30 MVA transformer block that will do anywhere from 10 kV to 34.5 kV, 50, 60 hertz. Same thing, lightweight, 50-ton crane can lift it up. We can put them into all sorts of aircraft if we need to move them fast. We don't necessarily have to put them into Antonovs. We can put them into Aleutians. We can put them on 747 freighters. Gives us a lot of flexibility. You've got N+1 redundancy as well. You lose a transformer, you're not losing a 30 MVA transformer, you're losing a 10 MVA single phase. And you take that up onto the right-hand side. Here we have our single phase transformers again, but these are high voltage transformers, they're oil filled, and it's a 70 MVA block. You have to go into oil at those voltages. That transformer system will then take 33 kV or 34 kV all the way up to 138 kV, 60 hertz. That has to be done inside oil. And doing it in a 20-foot footprint, flexibility, ease of movement. We don't have the challenges of not having roads and bridges to be able to take the weight of bringing in a 70 MVA power transformer. You're coming in with 35 ton of transformer dry with all the accessories taken off it. That's workable, it's doable. Infrastructures in the countries can handle that. You come in with a 150 ton transformer, that creates a lot of challenges. You need the trailers to put it on, you need to find the cranes to move it. It just becomes a logistics challenge. So what we see up on the front is power generation. Everything else then comes in behind it. It's all the challenges of dealing with it. Design engineering, the logistics, as I said, is a major, major challenge. Custom installations, local labor, maintenance, fuel guarantees, security, health and safety. We've got a very good health and safety culture in North America and in Europe. When you go into the developing world, it's not there to the extent that we have it here because it's a cultural thing. We want to see our mom and dad coming home from work every day. It's not that the fact that they bring home a paycheck and there's food on there, we actually want to see them come home. And hence that drives a very, very strong cultural health and safety environment with us, whether it be with the environment, whether it be on the work industry. And some of the challenges we face are fuel storage, quality of that. The customer has the fuel storage. It takes time to build millions of liters of fuel storage. If the customer has it, we can leverage that. But is it usable? Has it been maintained? Is it full of garbage? Is it leaking? It's all the challenges that you have to accept when you're going in and you're doing a temporary project. Fuel quality. A good example here, on the very left-hand side, we see some pretty decent fuel. This is a product that came out of Japan after the Fukushima incident. We had 200 and something meg on the ground, of which half of it was MTU power modules. And then we take it to the second site, and the other two vessels there on the left-hand side are showing the local quality of the fuel that we picked up in the developing world. Which fuel would you prefer to run on, the right side or the left side? It causes challenges. Your engines don't run. You're eating through filter media faster than you expected. Does the customer have somewhere for you to interconnect into? The substation is damaged or blown up or non-functioning. In this case, this is a 33 kV substation that was completely damaged. Customer is bulldozing it out of the way, and we're going to connect right in on top of their 30 kV bushings and put the power back up on the grid with them in weeks instead of them waiting, as we know, 6 to 8 months to get new switchgear manufactured and then get it to the country, get it installed and commissioned. Space is also a challenge. Large blocks of power need large amounts of space, whether it be gas turbines, whether it be gas recips, whether it be diesel recips, and all the balance of plant that goes around it. You can't put it in a shoebox, you need space. And the challenges with space is, when we look at efficiencies of diesel engines and gas engines today, if we're running 40% on a diesel engine, 44% on a gas engine, all the rest of that is going up as heat into the atmosphere. So you put a 100 meg block on the ground, you've got nearly another 100 meg of waste heat in the atmosphere, raising your ambient temperatures, which now your cooling system has to deal with. Your air filters are dealing with it because the engine's now seeing hotter air. Are you derating the engines? It's all performance. And it all affects the total cost of the kilowatt in fuel efficiency. Is the site suitable? What are the challenges? Now we have the space. We have to do a massive amount of civil works to make the space usable. Take out old foundations for an old power plant, go down 4 or 5 meters, take it all out, get it leveled, compact it again before we can even bring our power plant in. Fuel treatment, having the right assets. Correct filtration. It's a lot easier to do redundant fuel systems and address fuel at 150 liters a minute, 150 liters a minute, and instead of going down to the engine and having to change rake cores on 100 engines and change the primary filters on the engines as well, address it up front. As the fuel's coming off the trucks, aggressively treat that fuel, pull the water out of it, pull all the contaminants out of it, and make our lives easier for preventive maintenance on the power plant. Interconnecting with the customer. Normally, when we talk about it, it's what's the voltage? And can we connect in? So we have to have the solutions for that as well. So an example I was showing you earlier with the single phase, here's a 3-phase power transformer. It's a 100 MVA, 66 kV transformer, and it's about 200 tons when fully assembled. You have to have concrete foundations to support it. You have to have all the T&D around it to get that power off the transformer up into the grid, which is on the right-hand side there. These are dead tank circuit breakers. And in this instance, we're using 145 kV circuit breakers because the transformers are tappable. So our philosophy as a fast-track company is we buy assets that are very, very flexible. So when we're looking at distribution class voltages, everything I do is in 40 kV class. I can use it for 10 kV, I can use it for 25 kV, I can use it for 33, 34 kV. Same circuit breaker can be used across. Then the next big chunk we go into is 145 kV. I can use it for 60, 66, 90, 110, 115, 138. It doesn't matter. Its current rating is good, and the voltage class is good. The only thing that we have to do that's custom is what's sitting up here on the top of the transformer, which are the surge arresters. We do not like getting hit by lightning. It does a lot of damage, and I'd sooner have the surge arresters take that hit and trip our circuit breakers than damage the transformers. So technology. Libya is a very good example of rapid deployment, distributed power. 500 meg at ISO conditions, 450 meg at site conditions, 6 sites, lots of interconnects on all 6 sites. We did turbines with 2 interconnects at 66 kV, Caterpillar power modules, 2 interconnects at 66 kV. The rest of it was all gas turbines interconnecting with single interconnects into their grid at 30 kV, all done in 75 days once the equipment arrived in country. All the challenges of working in a country that's come out of civil war, trying to get local support, local employment, logistics companies, working with the utility. Do they still have drawings? Do they still have the information for their substations? How are we going to do all this? Working down in the middle of the Sahara Desert in Samnu and Barak. Really, really hot. The hottest I've ever worked in my life down in Barak. I'm drinking twice this every 15 minutes. 55 degrees when we're commissioning the plant with 100 meg of diesels running, with another 100 meg of heat going up into the atmosphere, with 45 degree local ambient temperatures being compounded with all the waste heat coming off the generation. That was our biggest risk on these projects, was health and safety of all the employees and all the staff on site. Do we have enough water? Is everybody drinking enough water? Watching buddies, hey, you drinking your water? it's dangerous. Aside from all the other challenges of working in the country, from that's just come out of a civil war, it's just even the health and safety due to the ambient conditions. So remote monitoring, everybody talks about smart grids, big data. When you start putting down large quantities of generation, this example I'm showing you is for gas recips. We all know how many sensors are on a V16 engine, exhaust gas temperature probes, monitoring ignition coil voltages, monitoring NOx sensors. You multiply that up, how does one person monitor a power plant to make sure everything is running correctly? We don't. We use smart software, collect all the data in off all the gen sets, run algorithms on that data as it's coming in, looking for anomalies. Is this engine, the knocking happening too frequently, the levels of the knocking, the restriction on the air filters within specification, is this delta P's across our fuel filters, is that okay? The gas filters, do we have any gas leaks? You can't look at that with human intervention. You have to use software today. This example, we're looking at probably 20,000 real-time data points coming in, all being archived historically, but giving us good intelligence and also helping us do predictive maintenance on the engines. Take the engines down when we need to so we can manage our labor force on the site and have what we call unscheduled outages, surprises. We do not like surprises. We want to manage the maintenance and do it in the day shift, and we do that by doing predictive analysis. Do we have enough left on the air filters to get us through to the next shift? What's the risk? Historically, with site conditions, yes, we'll make it another 24 hours. Take the engine down. Is it coinciding with oil service intervals? Is it coinciding with the valve lashing? Doing oil analysis, putting labs on the site. The amount of return on investment with all this technology is great. Being able to do our own oil analysis on the site. You know, there's lots of companies here in the US, Caterpillar, SOS Labs, Intertech, all the different other labs that are doing it, but putting it on your own site and not having to deal with the logistics of getting oil out of country to a lab to get it analyzed to make sure that the health of your engine is good. It's like going to your doctor once a year and getting a blood checkup. You want to know the results within days, not weeks or months, because if there's something wrong with that engine, you want to know it now. And we all know what the cost of a 16V engine is from all the engine manufacturers. It's not cheap. And a replacement is not cheap. And it's downtime, it's lost revenue as well. So collecting all the data, it doesn't matter if it's gas recips, diesel recips, or gas turbines, same thing. Bring in all the data, analyze all the data, generate KPIs. When we talk about turbines, it's all about efficiency. We're burning massive amounts of fuel per minute on a 25 megawatt turbine. Looking at all the statistics off of that turbine, do we need to do what we call a water wash? You're pulling in massive amounts of airflow, even through air filters, and trying to get that air as clean as possible before it hits the compressor, but it's still going to foul up. If it fouls up, it's going to affect your heat rate. You're burning more fuel to make more energy, to make the same amount of energy. Using statistics, we can analyze and say, we need to take the turbine down, do a water wash on it, bring it back up, and now our fuel efficiency is back where it needs to be. But to do that, you need to know exactly what's coming in. So using mass flow meters, whether it be liquid or gas, using weather data, we need to know what the ambient site conditions are. Are we within our specifications for what we're guaranteeing to the customer? When we talk turbines, we're talking 15 degrees Celsius. So we cross-reference everything back to 15 degrees and show that we're compliant. You need very accurate energy metering, and that goes into the current transformers and the voltage transformers as well. It's not just the meter, it's the full system. So now you've got a very accurate measurement of your fuel coming into the power plant. You've got very accurate information of the energy going out, how much you're producing, and you know your climatic conditions. Are we compliant with our contract? The reason that's important is if you're paying 16 to 18 cents a kilowatt hour, I'm charging you 4 to 5 cents for the power plant to convert that fuel into electricity. The biggest chunk of the money is the customer's fuel cost. And if I'm not fuel efficient, it's costing them a lot more money to produce that kilowatt than my competitors. So we have to be very, very cognizant on fuel efficiency on the system. And with that, we'll take questions.
Yes? You talked quite a bit about the cost, and you
Yes, we do. You're dealing with sovereign governments, you're dealing with prime ministers, you're dealing with energy ministers, and we have a very good reputation of doing what we say we will do. We will deliver you power, we'll do it for you efficiently, and we'll do it for you on time. I expect to get paid on time as well. We're putting money back into your country with employment, and being a US-based company, we are very good friends with the US State Department and everywhere we work. And if it means getting the ambassador involved to have a chat with the local government going, guys, you're interfering here with US interests. They've done their job, they need to be paid. And then we all take money home and feed our families. The locals get paid, they feed their families. So it has to generate revenue. If it doesn't, we're not in business. Yes?
Wait.
What's your security setup in a place like Libya?
Challenging. You're working, in Tripoli it wasn't so bad. GCall, who's the local utility, had its own security force. We had our own security over that, monitoring it. When we got down into Samnu and Barak, we actually worked with the local, for lack of a better word, militias, and made them understand who we were, what we're doing, why a bunch of white guys are running around in their territory. We're putting power on. Once they saw the lights come on and the grid stabilize, it's pretty quiet. But it's a very, very good question. It's part of our health and safety culture. Our employees on the site, regardless of their nationalities, local, foreign, have to be in a safe working environment. If they're not, you can't do your job. This is a more recent install. This is a nice drone shot of a plant we did in Bell Bay in Tasmania. They lost their subsea cable to the mainland and lost a couple of 100 meg of capacity. At the same time, they were going through a drought, no water for their hydro. And Tasmania is very, very environmentally sensitive. They like to do a lot of hydro. They don't like doing thermal power plants. But we came in with a solution with our turbines running on diesel initially and then switching over to natural gas, and also doing what we call water injection. So we're using demineralized water being injected into the turbine and reducing our NOx footprint on the site. Down on diesel about 42 ppm, and we went over on the gas 15 ppm by just adding water in with the fuel. And the reason for demin is the turbines are very sensitive, they're aircraft engines, and you want to make sure that everything that's going into that aircraft engine is squeaky clean. Otherwise, you're just going to destroy the combustion system.
Question?
Yeah.
You mentioned it when you talked about transformers.
Yes.
And the issue there was the flexibility of those transformers because
Correct.
you're watching your balance sheet. And my question is kind of related to that. Your company must have a giant balance sheet. How's it been since you have become now privately held? And has that contributed to your flexibility and your ability to perhaps take risks and do other things? Thanks.
I wouldn't say we take risks. Everything is calculated. You look at the finances on a project per project basis. We run a bill of materials. We know what the capex is for all that. You know what the rate of return you want on it, and can you be cost competitive against our competitors on a cents per kilowatt hour to do it. Transformers are actually not that expensive when you look at it on a power plant scale. The big transformer that we showed you there in the picture, it's about the same cost as a cat power module. I need one of those, but I need 75 cats. So it's a different scale. So what we find out over the years when we look at our finances is the biggest asset value we're carrying on our books is actually the power generation asset. It's not all what we call the BOP, all the glue material to make the power plant work. It's the actual generation assets and where the money is. Yes? Yeah, that's a very good question. I mean, heat recovery is definitely beneficial in overall efficiency of a power plant. But when you're going in to do something temporary, trying to put heat recovery, HRSGs, heat recovery on exhaust systems on recips, it's not practical. And the other main reason for that is there's no use for it. So we're out in a rural area because we're outside cities. There is no industrial application that can take the waste heat from us. So it's get it on the ground, get it up and running, and produce energy that the country can afford. Ideally, when you go into a permanent solution like this, the video showing here on Bell Bay, that's a thermal power plant with full heat recovery, and they're probably running when it was operating, they were probably in the 55% efficiency. You take that same thought process, you take it into Europe, they'll take all the additional waste heat and put it into district heating in the winter months. And now they'll really start pushing their efficiency on the power plant versus the amount of fuel that they're taking in. Any more questions? Yes.
So I understand that the majority of your projects are in developing countries where
Correct.
the emission standards are much lower. Have you done any projects in more developed countries where you have higher emission standards?
Yes.
How do you deal with that?
Best available emissions technology. Example, going in with TEPCO and putting in 200 meg right after Fukushima, we did SCRs on all the recips, and we did water injection on all the turbines. When we went into Uruguay, customer elected to take turbines over recips because we could give them a better emissions footprint for the overall emissions footprint on their power plant. So it was taking it in a larger vision. You have emissions compliance if you're a standalone power plant, but if you're going into an existing power plant, that power plant has an emissions footprint it's got to stay in. And even doing the SCRs on the diesel recips, we couldn't meet the requirements. So the customer was willing to take more expensive, higher heat rate on gas turbines to get cleaner emissions and be more environmentally friendly. So it's customer to customer on what their priorities are. Some people, some governments, some countries just want to have power on. Emissions is the last thing they're worried about. They want to stay in power, they want to stay elected, they want electricity on. And other countries, emissions is everything, like we have here in the US and Europe. If you're not emissions compliant, the EPA is not the person you want knocking on your door.
Yes, especially when you're working in developing countries where you're maybe trying to stabilize a grid,
Yes.
meaning you're not the only person contributing to that grid. How hard is it to communicate, cooperate with other power generation facilities, especially when it's expanding maybe over a couple of sovereign territories?
When we're connecting to the grid, we're going to what we call base load. So the two things we're monitoring on the grid is the frequency on the grid and the voltage. With different technologies and control systems on the turbines or on the recips as well, we can do what we call voltage support and we can do frequency support. So an example of what I mean by that is if the frequency starts going over 60 hertz or 50 hertz, you've got too much generation capacity online. Frequency goes up. If the frequency goes below 50 or 60 hertz, you've got too little generation. So you can control within your control systems on the power plant and try and maintain 50 hertz if the grid's unstable. Same thing applies when we're looking at grid voltage. If the grid voltage is too low, we turn on what we call our voltage support mode on the turbines or on the recips, and we add VARs into the system and we bring the voltage back up to where it needs to be. And depending on the countries we're operating on, example would be Argentina. Grid codes there require us to be able to do voltage support. If we're not, we're penalized financially in our invoicing monthly. They're not looking for frequency support, they're looking for voltage support because we're out at the end of the grid.
Another facility decides to use you as the pack mule as they take maybe some of their capacity down for maintenance or whatnot.
If they take it down, the grid's going to fall. Your direct impact of taking capacity off the grid is frequency reduction. When you're talking about power quality, that's why we have surge arresters on the system. So they're on our interconnection point with the customer, and then we have surge arresters on every critical asset that we have on the power plant, on the transformers, on the T&D, and on the high voltage side of all our transformers. Even if we're doing, let's say, a pad mount, 2.5 MVA, stepping up a diesel power module to 13.8, we have surge arresters on every transformer. So that protects you from events on the grid using very, very well-programmed protection relaying, whether it be Schweitzers, ABBs, Schneiders, it doesn't matter. They're all very, very fast-acting relays. You're looking at what's going on, and you want to be able to clear yourself off of the grid very, very fast. So you're looking at the closing times and opening times on your circuit breakers, the response time on your protection relaying, the delays you have built in there. You don't want to be tripping off, nuisance tripping all the time, but if there is an event out there, you want to be off the grid really fast and protect your assets. All right. Pleasure presenting to you this morning, and I'm around today and I'm around tomorrow and gladly answer any questions if anybody else wants to do any one-on-one. And thank you very much.
Thank you, Edmund. Very insightful presentation. I think also an eye-opener for our members who don't typically play in that space in our industry. So I think we did a good job educating membership today with that presentation. Also some very cool images and videos. So thank you again, Edmund. Also thanks to Dave Stringer from DIFE and Vaughn Beasley from Ring Power for helping to kind of pave the way, making the connection to Edmund for us this morning. So thanks, guys.